সরি, আনমিউট করতে ভুলে গেছিলাম। ওকে, সরি। ওকে, সো yeah, okay. So let us continue to prove this theorem that for a non-empty set A of a group G, where the L angle R angle A is the smallest subgroup generated by capital A, right? In the group G, then our aim is to find out the elements of that group. How do they look like, right? So how can you designate one element of this group, subgroup, right? So what are the elements? The elements can be designated as that it is the product of A1, A2, An, finite product, where An is a positive integer, and for each k, ak or ak inverse belongs to A. Okay, okay. Okay, so finite product of elements A1, A2, An, where each element or its inverse will be taken from the set A. Okay, that we need to prove. Okay, so what is the scheme of the proof? So first of all, we need to define this set first, right? So let H is the set of all those finite products n belongs to Z plus, where for each k, ak or ak inverse belongs to A. Okay, okay, fine. Then note that every element of A must be in H, right? By the definition of H, you can say that every element of A must be in H. That is, A is a subset of H. Okay. Now we are aiming to prove that this H is a subgroup of G containing that A, right? So H is a subgroup of G containing A. So how to prove that H is a subgroup? Suppose you are considering two elements. Suppose you are considering X and Y belongs to H, so that X can be written as finite product of A1, A2, An. Y can be written as finite product of suppose B1, B2, Bm, where by the definition of H you can say that where AK or AK inverse belongs to A, Bj or Bj inverse belongs to A. Now let us look at the element xy inverse, because once you prove that this element is in H, so this implies H will be a subgroup. So xy inverse means A1, A2, An, and then you write down B1, B2, Bm inverse. That means A1, A2, An dot. Now, what is the inverse of this product? So it will be from the reverse side. That is Bm inverse, Bm minus 1 inverse, B2 inverse, B1 inverse, right? So as a whole, if you consider this element, then you can say that each of the element or its inverse is in A. So therefore, this belongs to H. And this proves that H is a subgroup of G containing A. Okay. So H is a subgroup of G containing A. Now, by the definition of L angle R angle A, so that subgroup is the smallest subgroup containing A. So being smallest subgroup containing A, we can say that L angle R angle A is contained in H, right? Okay. So in this way, you have proved that this subgroup must be in H. But we need to prove the equality. That means actually the smallest subgroup generated by A is H. Okay. And for this reason, okay. So note that again, we see that for subgroup, for any subgroup, capital K containing A, we have we have uh, we have for all A belongs to capital A and its inverse belongs to capital K, because being a subgroup. One minute, please. একটা ফোন এসছে। Okay. Okay. So being a subgroup of G, if you take any element A, then that A, this small a, is in K, and being a subgroup, so A and A inverse both are in K, right? So then you can say that, so taking any finite product A1, A2, N, right? So this uh, where either AK or AK inverse belongs to capital A. Okay, yeah. Sorry, belongs to K. I'm sorry. Yeah. So A1, A2, AN belongs to K. So that product, but this product is in H. So this implies that any element of H, if you take any element of H, which is a finite product of elements or its inverse, belongs to A. So this implies that H is a subset of K. So in this way, this proves that H is the smallest subgroup containing A, and this proves that H is the smallest subgroup of G containing A, and hence, but we have defined that the L angle R angle A. So hence H equals with this one. Okay. So this proves that the subgroup generated by A contains elements of this type. Any finite product of elements where each element or its inverse belongs to capital A, right? So that means any finite product of elements or its inverses are in this one. Okay, right? Okay, okay, fine. And note that uh, note, let G be a group and A subset of G, be any subset. If we define A inverse, what is that? It contains those elements which are inverses of the elements of A. That means A inverse, where A belongs to capital A. Just take inverse of each element and put it here. Okay. So one can say that this is the set of all inverses of A. Okay. So then one may prove that the smallest subgroup generated by A and the smallest subgroup generated by A inverse both are same. Okay, both are same, right? Okay, fine. Okay, in this context, we have seen some beautiful features of the operation on a class of groups. That means we are talking about intersection of class of groups, class of subgroups of a group, right? And we have seen that intersection of a collection of subgroups of a group will be a subgroup. But what is the outcome whenever you are taking union instead of intersection, right? Now if you consider union, okay, so the problem is that, okay, so let us have a look at this example. Which one? This is a very common and very well known example in this context. So we have seen that the subgroups of z plus dot z plus, the subgroups of z plus, what are those? These of type nz, right? N is greater or equal to 0. So either it is singleton 0 or it is of the form nz n greater than 0. That is either singleton 0 or nz n greater than 0, right? So these are all the subgroups of z plus. Okay. Now you consider any two nz. Suppose in particular take 3z and 5z are subgroups of z plus, right? So we are considering two subgroups. Now what about their union? And let H is the union of 3z, 5z. Now the question is that, does it form a subgroup in z plus? Again, the answer is no, because here you see that 3, so 3 in 3z, and being in 3z it must be in H. Similarly 5 being in 5z must be in H. But if you consider their sum, because whenever we are talking about subgroups, the operation must be closed, right? So that operation plus, will it be closed in H? The answer is no, because the sum of 3 and 5 is 8, right? So if 8 will have to be in 3z union 5z, then you need to have the conclusion that 3 will divide 8, 5 will divide 8, right? But that is not the case, because 3 and 5 both are prime numbers. So 3 plus 5 will not be in 3z nor in 5z, right? Because if it is in 3z, then 3 must divide 8. If it is in 5z, then 5 must divide 8, which is not the case. So 8 does not belong to 3z union 5z. So that means that, so this operation is not closed here in 3z union 5z. So hence you may conclude that 3z union 5z will not form a group, will not form a subgroup, okay, of z plus. So it fails to be a subgroup of z plus, right? So just in the case of two subgroups, the union doesn't satisfy the property. Okay, but but the interesting fact is that the union of two subgroups will be a subgroup if you impose one condition that either of them is contained in the other, right? So the result is that theorem that let Hk are subgroups of a group G. Okay, then the statement is that H union K is a subgroup of G if and only if either H is contained in K or K is contained in H. That either of them will be contained in the other. So that is the condition, and with respect to which H union K must satisfy the property of being a subgroup of G. Okay. So why this condition comes into the picture? Because now if you take this condition will be satisfied by H and K. Okay. Then suppose H is contained in K, then H union K will be only K. So it must be a subgroup, because if you have considered K to be a subgroup, right? So it is obviously a subgroup. And in the other case, if K is a subset of H, then H union K is H and H is a subgroup. So you do not have to worry about that. But for the converse case, for the converse part, let H union K forms a subgroup. Okay. So it forms a subgroup of G. Then what's to be done? So assume that so you need to show that either one of them will be satisfied by H and K. That is, either H is contained in K or K is contained in H. If not, suppose H is not contained in K, what does it mean? Implies that so H is not contained in K, that means that there exists a small h belongs to capital H such that H will not be in K. Okay, fine. Then for any small k belongs to capital K, what will you get? Then uh, you see that, okay, so yeah, then for any a we see that yes, H belongs to H, K belongs to K, implies so H K in H union K, right? H and K are in H union K, and being a subgroup, because you have assumed the condition that H union K forms a subgroup, so that means the operation is closed over H union K. That means if you compose H and K, then it will be in H union K. Okay, so that means since HK is in H union K, so HK must be either in H or in K. Okay? Okay. Now, if HK belongs to K, then what would be the case? Then you see that H can be written as HK K inverse, right? Right? So that means HK belongs to K and K inverse belongs to K. So it is in K. So H is in K, but you have assumed that H is not in K, right? So this contradicts that fact. So a contradiction. And this contradiction implies that HK must be in capital H. It is not in K. So it is in capital H. And this fact implies that so K, small k, can be written as H inverse HK, right? And which leads to the conclusion that HK belongs to capital H belongs to capital H, so that means it is in capital H. So for any k, that k must be in H, and this implies k is a subset of H. So whenever you have assumed that H is not contained in K, then the assumption H union K forms a subgroup implies that K must be in H. K is contained in H. Okay. So one of the two cases must hold, that either H is contained in K or K is contained in H. Okay. Fine. Okay. So one remark can be made here. So you have seen that. So for a group G, two subgroups are H and K, suppose. Okay. So in general, H union K may not form a subgroup of G. Okay. So in general, H union K may not form a subgroup of G. But if you consider the intersection, then it is H intersection K is always a subgroup of G, right? Okay. Okay. Not only that, H intersection K is the largest subgroup of G contained in both H and K. Okay. So H intersection K is the largest subgroup of G contained in both H and K. And also, as we have seen that H union K in general, it will not form a subgroup of G, but considering H union K, you can construct a subgroup containing both H and K. That is the smallest subgroup of G containing H union K. Okay. Also, one may construct a smallest subgroup of G containing both H and K, right? Okay, okay, yeah. So one may construct a smallest subgroup of G containing both H and K, and notably, yes, yeah, okay, yeah, okay, okay. So yeah, now now suppose I'd like to define two things, that let G be a group and suppose H, K are two subsets, okay, of the group. H, K are two subsets of this. Okay. So H and K are two subsets of G defined to new objects HK, right? It is a set of elements of the form HK, small h composed with small k, where small h is taken from H and small k will be taken from K. So that is the definition. So taking any two subsets H and K, is just consider their product. Okay, and H inverse is, yeah, okay, okay, fine, okay. Now note that for a non-empty subset, H of G, H forms a subgroup of G. H forms a subgroup of G if and only if H will coincide with H inverse. Okay, H will coincide with H inverse. Okay, that you need to check on your own. That is a exercise. That is an exercise to you. Okay. Now we are going to prove that the result is that the result is that what is the result? Now taking two subgroups, okay, let H K be two subgroups of G, of a group G, of a group G, okay. H and K be two subgroups of a group G, then HK will form a subgroup. HK will form a subgroup of G if and only if HK will form a subgroup of G if and only if HK equals with KH. So that is a very nice property, very nice thing that is happening here. That HK will form a subgroup if HK coincides with KH. Okay, and not only that, then HK is the smallest subgroup this is the smallest subgroup of G containing both H and K, both. Okay. So this will be the smallest subgroup of G containing H and K. So you have seen that I have written down on my construct a smallest subgroup of G containing both H and K. And one may tempted to think that this smallest subgroup may be the smallest subgroup generated by H and K. Not, it is not. Okay, because uh, so yeah, it is need not be H union K. Okay, it contains, one may construct the smallest subgroup of G containing both H and K. Need not be H union K. Okay, because the smallest subgroup generated by H union K will be different from the smallest subgroup of G containing both H and K. Okay, and what is that? That is the HK that we are going to prove. Okay, so the proof is that so the proof is like that. Yeah. So suppose HK forms a subgroup of G. Okay. Then the observation that I have written down here, this one. So with respect to this observation, in view of this, you may say that HK HK, 1 minute, equals with HK inverse, right? HK equals with HK inverse. Uh, 1 minute. Yeah. I think this will be mm, no. This will be this one, right? Okay. Yeah. H equal to H inverse. Yes. So then HK inverse can be written as K inverse H inverse. Why? Just taking any element of this, that is K inverse H inverse belongs to K inverse H inverse, implies. Now K inverse H inverse is HK inverse, right? So it is K inverse H inverse, but HK inverse is in HK inverse. So that means, and this is if and only if. Okay. So this implies K inverse H inverse equals to HK inverse, right? Okay, fine. And since K and H both are subgroups, so K inverse is K, H inverse is H. In view of this, yes, this one. Okay, fine. Conversely, suppose that HK equal to KH holds. Then HK HK inverse, okay, implies HK HK inverse. 1 minute, 1 minute. I think no. Sorry. This is true. This is true. Sorry, sorry, sorry. This is true. Yes. Also note that H is a subgroup. If and only yes. This also holds. Yes. H is inverse. Yes. Yeah. From this observation, just yes, this one. Okay. But this is true also. Yeah. This one is also true. Okay. So then HK inverse equals to HK, and this is K inverse H inverse, right? That means K inverse, and it is H inverse using associativity. Using associativity, you may write that for any three subsets, suppose P, Q, R of G, PQ R equals to PQR. Using associativity. Okay. Okay. So then what is K inverse? Now since K is a subgroup, so K inverse is K from this result, this observation, this, okay, that k inverse is k. So it is hk H inverse, right? But what is hk? Hk is kh. So it is kh H inverse, and then again considering associativity, you will have this is H inverse. And since H being a subgroup, so it is kh. Then kh is equal to hk. So you have seen that hk satisfies the property that hk equals to hk inverse. So in view of the same observation, you may conclude that hk forms a subgroup of G. So that you need to prove that observation, that H, if H is a non-empty subset of a group G, then H forms a subgroup if and only if H will be equal to H inverse. Okay, fine. And yeah, okay. So why it is smallest? Why it is smallest? Note that now since H and K both are subgroups of G, so the identity belongs to H and K both, right? And this implies that this fact implies that H can be written as H product with the singleton identity. And since this E is in K, so you can write it as HK, right? In a similar way, you can show that K is a subset of HK. So H and K both are in HK, right? Now, if L be any subgroup of G containing both H and K, then clearly L is any subgroup of G containing both H and K, then clearly their product HK must be in L. Why? Why it is true? As because of this fact, right? Why it is true? Because H is in L, K is in L. So if you compose every element of H with every element of K, then small hk must be in L, because L is a subgroup of G, right? So you have seen that if L is any subgroup of G containing both H and K, then that HK is the smallest. Okay. So thus, when you see that HK coincides with KH, then HK will be the smallest subgroup containing both H and K. Okay. So in this case, you have described the elements of the smallest subgroup containing H and K, which is of the form small hk, or small h taken from H, capital H, and small k taken from capital K. Okay. So one corollary you may consider here. Suppose you have an abelian group. So for any pair of subgroups Hk and abelian group G, Hk is also a subgroup, because in that case Hk coincides with Kh. It's also a subgroup of G, as because okay, that, yeah, as because Hk coincides with Kh being, so in an abelian group G. Okay, fine. Okay, okay. Now, yeah. Now let us give you some more examples of subgroups of a group. So how to generate new subgroups in a group. Okay. Okay. So let us have a look on that. Yeah. Normalizer, centralizer of an element. So let G be a group and you need to consider one element, small a. Okay. Okay. Then with respect to this element, you are defining one set. So we define a set denoted by C suffix a, which are which is consisting of those elements of the group G which commutes with A. Okay, suppose it is your G, it is a group, and you have considered one A. Then you are considering those elements which commutes with this. Okay, this one, x1, x, y, z, w. Okay, so which commutes with A, only A. In that case, just we are considering those elements of G which commutes with A. Okay. Now X may commute with others, but now we are taking the X which will satisfy that X commutes with A. Just putting uh, just emphasizing that A generates a set. Okay. Then it is clear that now identity element will always commute with others, right? With any elements. So then EA will be A, right? And that means so E belongs to CA. And once you see that identity lies in a set, in a subset of a group, then you need to check that whether this subset will form a subgroup or not. Okay. So now for suppose XY belongs to CA, sorry, CA, we see that now X and Y is in CA. So we see that so XA equal to AX, YA equal to AY implies so XYA equals to XYA using associativity. Now then YA turns out to be AY. And then again apply associativity and it will be XA Y. Then XA equals to AX. So it is AX and this is Y. Again applying associativity you have AXY. So that means XY commutes with A. So this implies XY belongs to CA. Okay, fine. Okay. Also, for any X belongs to CA, we have AX equal to XA implies now multiplying both sides of this equation with X inverse, then you have it is X inverse AX this side and this will be X inverse XA. That means X inverse A X and it is X inverse X A using associativity and this equals with X inverse A X and this is identity so it is A, right? And then again multiplying both sides by X inverse again, then you will have X inverse and it is A X inverse. So that means X inverse A, so it is X inverse belongs to CA. And this proves that the subset that we have defined is an interesting one. Why it is so? Because it forms a subgroup. So CA forms a subgroup of G with respect to determined by A by an element A belongs to G. This subgroup is defined to be CA is called the centralizer or some says that normalizer of small a, an element small a, centralizer or right. this one. Okay, fine. So in this way, you can generate one subgroup out of every element of G, right? Now you may extend your idea to generate subgroups with respect to just not taking any element. If you take one non-empty subset instead of taking any particular element small a, if you take any subset of G and define, suppose 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 capital A be a subset of G, okay, and define a set denoted by C suffix A, sorry, which is consisting of all those x belongs to G, which commutes with every element of A. In the previous case, it consists of those x which commutes with the single element A. But in that case, we are considering all those x which commutes with every element of that subset. That is xa equal to ax for all A belongs to capital A. Okay. Then obviously again you see that E belongs to Ca because Ea equals to A for all A belongs to A. E being an identity of being the identity of the group, right? And then again for any xy belongs to Ca, you see that x y inverse xy sorry A is going to be xya, and this is again ay, and again xay, it is axy, and it is axy, and this is true for all A belongs to capital A. Not only that, and also ax equal to xa implies x inverse A equal to ax inverse, right? And these two together will imply that Ca forms a subgroup of G determined by capital A, and this subgroup is called normalizer of capital A or centralizer of capital A, whatever you think good. Okay, okay, fine. In this connection, I need to give you one description of another subgroup, that if you consider any group, then you can always talk about this subgroup without referring to any element or any subset, right? What is that? That is the center of the of G. Okay, center of G. So how can you define this subset? So let G be a group and define a set denoted by ZG. What is that? It consists of those elements of the group G which commutes with every element of the group, such that xa equal to ax for all a belongs to G. We are considering those x which commutes with every element of G. Now you have such an element, for example, identity. Identity commutes with every element of the group, right? And there may be others in the group. Maybe you can find one non-identity element of the group which commutes with every element of the group G. Okay. So using this idea, you can define this subset. And not only that, this subset has some special properties and which will be uh, taken care of uh, by our lectures in the discussion whenever we are talking about homomorphisms, automorphisms, then you will see that this subgroup has some special characteristics. Okay. Okay. So note that E belongs to ZG as because EA equal to AE for all A belongs to G. Okay. Okay. Fine. Then now let XY belongs to ZG. Then XA equal to AX, YA equal to AY for all A belongs to G. Okay. So this implies that XYA equal to XYA and this is XAY. Then applying associativity, it is XAY. And again in the same way we have done before, it is AXY and it is AXY. So that means XY belongs to ZG. And also in a similar way as above, for all X belongs to ZG, X inverse belongs to ZG, right? So this proves that ZG is a subgroup of, of the group G, okay, which is called the center of the group. Okay, so this is called the center of the group. Okay, and this group is not only a subgroup, this has some special kind of subgroup property and which will be discussed in our later discussions. And this subgroup will be a normal subgroup. No, it's not a general subgroup. It has some interesting feature. It will be a normal subgroup. Okay. So okay. I'll be talking this subgroups later. Okay. Uh, fine. Fine. Now note that note that G be an abelian group if and only if its center ZG coincides with G. Because in view of the definition of ZG, the center of the group, you will see that the center of the group consists those elements of X, those elements of the group G, which commutes with every element of G. So if G be abelian, then any element will commute with every element of the group, right? Because since for any A belongs to G, or any X belongs to G, Xa equal to Ax for all A belongs to G implies X belongs to ZG, right? Now ZG being a subgroup of G, so G equals with ZG. And on the other hand, if G equal to ZG, that means then for any two elements xy belongs to G. Now xy commutes with yx, sorry. So x and y is equal to x. Okay. Okay. So this shows that, so if G be an abelian group, then its center coincides with the whole group. Okay. Okay. So with this one, I would like to end today's lecture. Okay.